Alright, hello everyone, how are you all doing? So, today I'll be discussing the solutions to Google Kickstart 2021 Round G. This contest was held earlier today, and as always, the problems were really interesting. I would say the difficulty level was well balanced, with the first three problems being solvable, whereas the last problem being very hard, as it is always the case in a typical Google Kickstart round, right? So, yeah, I'll be discussing the first three problems fully, and I'll also be talking a little bit about the first subtask of the last problem. So, yeah, without any further ado, let's start solving the first problem. And yeah, so the first problem is called dogs and cats, and it's worth just 11 points, and that is justifiable because really the problem is very easy. There is nothing much to talk about here, but I'll still be going over it. So there are n animals, and some of them are dogs and some of them are cats, and you have food for them. You have D portions of dog food and C portions of cat food, and basically you just start giving everything one by one, and finally you need to tell whether you can give all the food items to all the dogs or not, right? So that is the case with just one twist, which is not really a twist, and that is whenever you give a dog some food, then you receive an extra m portions of cat foods, right? So that is the only extra thing here in this question, which is still not very extra because you don't need to do anything specially for it. Just add a similar condition, and yeah, so basically nothing special needs to be done here. You just iterate from 0 to n minus 1, and if it is a cat, you simply check whether you have any cat foods remaining or not, and if you do, then you just decrement your cat food by 1 and move forward. If it is a dog, then you check whether you have any dog food remaining or not. If you have, then you decrement your dog food and you increment your cat food by m, and you move forward. And if you don't have any dog food remaining, then you can't go any further. And finally you keep track of the index after which you can't go any further, and if there are any dogs which have not yet been feeded, then your answer will be no, otherwise it will be yes. So yeah, nothing extra needs to be done here. Just blindly do whatever is being mentioned in the problem and you'll be done. So let's have a quick look at the code for this. And yeah, so here it is. You take in the input for ndcm and you take in the string, and finally if you just encounter a cat, you check whether you have cat food remaining or not. If you do, well and good, otherwise you mark your index as I and break. Otherwise it's a dog, you check whether you have some dog food remaining or not. If you don't, you again mark your index as I and you break out. Otherwise you decrement your dog food but you increment your cat food by m, right? And finally you check for all values from index to n minus 1 whether there is a dog or not, right? So I have initialized index initially to n, so if we can feed all the animals, then nothing works inside this loop, right? So yeah, this is the simple solution to this problem. uh, Nothing very fancy here, so I guess everyone was already able to solve it. So without spending much time on this problem, let's move to the more relevant ones. So the first problem was really easy here, but all the other problems were interesting, and yeah, so it will be fun to know about them. So let's start with the second problem. So the problem statement is big, but basically what we have is we have been given with k rectangles, and we have all the information about the k rectangles, that is the leftmost point and the rightmost point. And finally we need to find a particular point such that if we keep a water bottle there, then the Manhattan distance between that point and all the other rectangles, the sum of the Manhattan distances, will be minimized, right? Now what the distance of a rectangle from a point means is basically the minimum distance you need to travel to reach that point, to reach any point in that rectangle, right? And you can only travel parallel to the axis. That is why that distance will be automatically equal to the Manhattan distance. Manhattan distance between 2 points is just the difference of their x coordinates added to the difference of their y coordinates, right? So yeah, that is the problem. You need to find a particular point such that your sum of Manhattan distance from all the rectangles is minimized. And yeah, so this is the problem, and let's start talking about the solution. First of all, looking at the test sets, in the first test set you can notice that all the values are really small. So let's see how to solve the first test set. So we are at problem B and TS1, right? So here what we notice is that your K is just 20, so you have at most 20 rectangles, and all these rectangles are in this region, that is their x and y coordinates are from -100 to 100. And another thing to note here is that for providing an information about a rectangle, you have been given with two points. One is the leftmost point, that is the bottom left corner, and other is the topmost point, that is the top right corner, right? So really what you have been given with is something like this. So for a rectangle you have been provided with this point and with this point, right? Yeah. Okay. So for test case 1 we can notice that the constraints are really small, and since all the rectangles are in this region from -100 to +100, what we can do is we can simply iterate on all points, right, and check for the point which minimizes sum of Manhattan distances, right? So this is the simple way to do it, and to find the Manhattan distance you don't need to do anything very difficult. Basically what happens is if the point is already in the rectangle, then the Manhattan distance is 0. Otherwise you just check for x and y separately. For example, let's say this is the first point and this is the second point, and you need to find the Manhattan distance from this rectangle of a point x comma y, which is located somewhat here, right? So you will realize that you need to move it first here and then here. So the answer will be just simply x minus x2 plus y minus y2, and similarly you can make all the cases and find out the Manhattan distance, and yeah, this would just work. So I don't think this is really relevant because this is just the first test set. The more challenging part comes when we look at the constraints for the second test set, right? So the second test set says that the number of rectangles is 10 to the 5, and the values of the coordinates itself is up to 10 to the 9. So these are really huge. So we can't really apply any sort of brute force here. We are forced to use some kind of observations here. So first of all, I'll be writing down a very well-known theorem. If you don't know this theorem, you should look about it on the internet, or maybe I'll be providing the proof here itself. So a theorem: to minimize the value of summation of modulo x minus xi for a given set of n values x1 x2 up till xn, we can place x at the median of all the given values, right? So this is a well-known theorem. That is, if you need to minimize this value of modulo of x minus xi for the summation of modulo of x minus xi for all I from 1 to n, where you are given the values of x1 up to xn, then the optimal value of x is just going to be the median. And let's try to see the proof, right? So although it's a standard property, I think proving it would just make it all the more clearer. So let's try to see how to prove this. Let's say we have some points like this. So we have 12 points, right? Yeah, 1 2 3 4 5 6 7 8 9. Yeah, so we have 12 points, and let's say we are somewhere here currently, right? So you can notice that the number of points which are strictly to my left is 3 and the number of points which are strictly to my right is 9, right? So if I move one step to the right, then the Manhattan distance, like the distance from all these points will decrease by 1 and the distance from all these points will increase by 1, right? So distance from here will increase by 1 and all the distances from here are going to decrease by 1, right? So really what is happening is moving one step to the right is proving to be beneficial for me, and the reason for that is that the number of points to the right are strictly greater than the number of points to the left, right? So as long as I have more points to the right than on the left, it is beneficial for me to move to the right, right? But once I reach a situation where the number of points on the left is greater than the number of points on the right, then moving one step to the right will not prove beneficial for me, right? Because the distance will increase for more points and decrease for less points, right? So basically I will just keep moving right until I have more points on the right, and there will be a point where I have equal number of points to the left as well as to the right, and that is the region after which I will stop moving, right? Because moving to the right will not be good for me. For example, if I reach here, then the number of points to the right of me is 3 and the number of points to my left is 9. So if I move one step to the right, the distance from all these 3 points is getting reduced by 1, but on the other hand the distance from all these 9 points is getting increased by 1. So in total my distance is increasing by 6, which is not good for me, right? But let's notice what happens in this region from the 6th to the 7th point, right? So this is the middle region, right? So as long as I am in this region, the number of points to my right and the number of points to my left is same, and also the summation of the distances is also same, right? Because if I move to the right by any small amount, then the distance from this 7th position will decrease, but this distance from this 6th point will increase by the same amount, and the same thing will happen for all these in pairs, right? So yeah, I have just proved that for a 1D system where I have n points, it is beneficial for me to be placed at the median, right? And this is a well-known theorem as well. So if you are into competitive programming, then you should really be actually knowing this theorem. Now, how to get through the solution of this 2D problem using this theorem, right? So the solution, right? And I'll be first writing down the solution and then I'll be talking more about it. So the solution is simple. You simply output the median of all the x coordinates and that of all the y coordinates. So now question arises that in the problem we have been given with two types of x coordinates, right? One is the x1 and one is the x2, which is the bottom left corner and the top right corner, right? Similarly, I've been given with two values of y, right? y1 and y2. So are they to be treated similarly or they have to be differentiated? So the answer is that we can treat them absolutely similarly, and there needs to be no distinction between them. And let's see why is that true, right? So let's see what actually is happening. So the trick here is to solve for x separately and to solve for y separately, right? So I'll be focusing simply on x and not on y. So let's take a similar argument. I am focusing just on x, and again I have like 12 points, right? Yeah, so I have these 12 points and these are just the x coordinates. Some of them might be x1s, some of them might be x2s, right? And let's say what happens in the region from the 6th to the 7th point, right? So this is that region. Now in this region basically divides all my points into two halves, that is the first half and the second half, right? Yeah, so in the first half there will be some x1s and some x2s. In the second half there will be some x1s and some x2s, right? And so there will be essentially some rectangles which will start in the first half and end in the first half itself. Like there are some rectangles like this, for example. Let's say this is the x1 value and this is the x2 value of a particular rectangle. Also there can be some rectangles which start in the first half and end in the second half. And similarly there can be some rectangles which start in the second half and end as well in the second half, right? Now I know that I'm in the middle, so the size of both the halves is same, right? So let's say size of both halves is s, right? So I know that in total I have 2 endpoints, right? For each of the rectangle I have 2 x coordinates, right? So this s is basically equals to n, right? So size of both the halves is n, so both halves contain n points. So out of which, and really what is happening here is some of the rectangles are of type 1, and these are these rectangles. Some of the rectangles are of type 2 which start in the left half and end in the right half. Similarly, some are of type 3 which start in the right half and end in the left half, right? Now out of which, let's say, yeah, so I know that size of both the halves is n. Let's say this is the first point. So in total I have 2 n points, right? And out of which, now I also know that any starting point in the any rectangle having the starting point in the first half and ending point in the second half will basically be a pair of 2 points, right? So and out of these 2 points, one lies in the first half and the second lies in the second half, right? So out of which the type 2 rectangles are k. Let's say they are k in value, right? So if there are k rectangles like that, that means there are k points in the first half and k points in the second half, right? So basically there are n minus k points in both the halves, right? So really what is happening is there are twice of n minus k points in both the halves, which means that there are n minus k rectangles in both the halves, right? And if I can use a similar argument. If I move one step to the right from this position, that means that my answer is going to decrease. And using a similar argument, I can say that if I am anywhere in this region from the 6th to the 7th point, then I have actually reached my optimal value, right? Because the number of rectangles which are strictly to my right is n minus k, and the number of rectangles which are strictly to my left is also n minus k, where k is the number of rectangles which begin in the first half and end in the second half, right? So since both these values are n minus k, I am actually at the optimal position, because even if I move right, my answer won't change as long as I am in this region from 6 to 7, right? If I start moving to the right from 7, then my answer is going to decrease. And yeah, so I used the argument similar to how I proved the theorem. So this just means that this solution is valid, right? I can just simply output all the x coordinates and take their median. Their median will just be one of these 6 and 7, right? And any these 6 and 7, the 6th and 7th point also lie in this interval, right? So this is an inclusive interval, so I can output any point which is in here, right? So why not just take the median? So yeah, this is why this solution works. You just sort all the x coordinates, sort all the y coordinates, and output the median. That is the middle element. So yeah, this is the problem done. And this comes up often in competitive programming, this theorem, so it is quite helpful to know. And let's just look at the code, and I hope you will be able to solve any problem related to Manhattan distance in the future, because mostly it's got to do something with the median, and that is a thumb rule. So yeah, let's look at the code. Code is simple. You just take all the points as input, and all the x coordinates you push into one vector, all the y coordinates you push into the other vector. You sort both the vectors and you simply output their n minus 1th element, since all of them have 2n elements. So the element at the n minus 1th index is going to be the median, right? Yeah, so this is pretty much it for the second problem. So it was an interesting problem, but moving on to the third problem. Again, this was a really good problem, so I'll be discussing this problem piecewise, that is from first test case, that is the brute force, to a little bit optimized version, to the highly optimized version. which is still O of n square. But anyways, so the question goes like this. So Barbara goes to Alan's banana farm where n banana trees are organized in one line represented by an array, and the tree at a position I has bi banana bunches, and each tree has a same cost. So we can say that the cost of each tree is 1, and if you buy a tree you get all the banana bunches that are on the tree. And the condition here is that you can use at most 2 contiguous sections of the trees, right? So basically you can choose just 2 subarrays from my array, and out of these 2 subarrays you take the sum, and the sum should be exactly equal to k, but out of all such subarrays you need to minimize the size, right? So that is the problem. Let's start from the solution step by step. Let's start from the first test set. Here the value of k is 10 to the 4 and the value of n is just 50. So according to the question we need 2 subarrays, right? So if n is 50, I can just iterate on all the subarrays. So let's start with the solution to problem C. So TC1, right? So first we'll be discussing the first test case. So here we realize that n is just 50, so the solution is simple. You can just use brute force, and that is just going to work. So what you do is you iterate on the first subarray and then iterate on the second subarray, right? So basically a subarray is defined by its starting point and ending point, right? So let's say that the first subarray is like I1 and J1, and the second subarray is of the form I2 J2, right? So basically if you find out that the sum of all the elements in I1 J1 and all the elements in I2 J2 is exactly equals to k, then this is the candidate answer, right? So if sum I1 J1 plus sum I2 J2 is equals to k, then you can say answer is equals to minimum of answer, and J1 minus I1 plus 1 plus J2 minus I2 plus 1, right? So the sum of the length of the first subarray will be J1 minus I1 plus 1, and that of the second subarray will be J2 minus I2 plus 1, right? So finding the sum of a subarray will take O of n time, and iterating on the first subarray will take O of n square time, and iterating on the second subarray will again take O of n square time. So the time complexity here is going to be big O of n to the 5, right? But you realize that that is still not enough, so you need to optimize on it a little bit, and you can bring down the time complexity from O of n5 to n4 using prefix sums. If you maintain prefix sums, then you can simply find sum ij in O of 1 time. That is pretty standard stuff, so I won't be going over it. And using prefix sums, the time complexity will be easily reduced to O of n to the 4, and this is actually enough to pass the first test set, right? So the first test set was kind of completely brute force. Everybody uses prefix sums, so that is kind of an understood thing, right? Yeah, so now I can move on to the second test set, right? So really what we are doing is we are iterating on all the 4 values, right? I1, J1, I2, J2. So now let's see how can we optimize this solution a bit more, right? So here what we are going to do is, instead of iterating on all the 4 values, iterate on I1, J1 and I2, but not on J2, right? So if you have iterated on I1, J1 and I2, basically you have the first subarray sorted, and like you have the first subarray in mind, and you also have the starting point of the second subarray, right? So all you want is that sum of I1 J1 plus sum of I2 J2 equals to k, right? And you already know this quantity. Let's say this quantity is like S1, right? So we want S1, like I am iterating on my I1 and J1, right? So this quantity can be treated as a constant. So I need S1 plus sum from I2 comma J2 to be equals to k, right? And I want the minimum value of J2 as possible, because the lower the value of J2, the better will be my answer, because I need to choose the minimum number of trees, right? So I need to find the minimum value of J2 such that sum of I2 to J2 is equals to k minus S1, right? And this can be done easily through binary search, right? So I can use lower bound. On the prefix sum array to find the optimal value of J2, right? And this is again pretty standard stuff. You can use lower bound, which will give you the first ever index where the summation from I2 to J2 will increase k minus S1. And to elaborate a bit more, sum of I2 to J2 will be nothing but prefix sum of J2 minus prefix sum of I2 minus 1. So if I want that to be greater than or equals to k minus S1, I want prefix sum of J2 to be greater than or equals to k minus S1 plus prefix sum of I2 minus 1. So if I do a lower bound on the prefix sum array of k minus S1 plus prefix sum of I2 minus 1, and if I actually find the value to be equals to k minus S1 plus prefix sum of I2 minus 1, then I will consider it as a candidate answer, and this can be done in log n time. So the time complexity here turns out to be big O of n cube log n, right? Because I'm iterating on the first three variables, that will be n cube, and log n time for the binary search. So one thing is that this binary search can be avoided with the use of 2 pointers, but that's not really necessary, because it is enough to pass the second test set. So yeah, that is it for the second test set. You can either use binary search or 2 pointers, that is up to you. I generally prefer the binary search because it's simple to code, right? So now let's look at the third test set. And this is where things start getting more and more interesting, because any approach you think of actually fails here, right? If you try to do an O of nkdp, even that won't work, because n is up to 5000 and k here is up to 10 to the 6, right? So there is actually a way to solve it in O of n into k. So that might be interesting, but since here the constraints are large for k, a natural thing to do here is to look for an O of n square approach, because n is up to 5000, right? So naturally one would look for an O of n square approach, and that is what I am going to be discussing now. So in our solution to the second test set, we were iterating on the first three variables, right? We were fixing I1, J1 and I2. But now let's say what happens if we fix just the first subarray, right? Fix the first subarray, right? That is, iterate on I1, J1, and while you are iterating on I1, J1, let's see what is happening, right? So instead of iterating on I1, J1, let's look at it in another way. So iterate only on J1, right? This is somewhat like the meet in the middle technique, and yeah, it is actually the meet in the middle technique that I'm going to be discussing right now. So you have 4 values. So what you do is you iterate on the second value, and magically this is going to help you, right? So if you are currently on a J1, you now iterate on I1, right? So after fixing J1, right, now iterate for I1, right? So you are iterating on J1, and one thing which you need to do is you iterate in reverse order, right? you scan your array from n to 1, right? And you are iterating for j1 and that too in reverse order. So you are at a particular value of j1 and you have scanned the array from j1 plus 1 to n already, right? And after that you will iterate on I1 and then you will have your first subarray fixed, right? But you know that you have already scanned the array from j1 plus 1 to n, right? So now I have scanned the array from j1 plus 1 to n, right? So let's say I define another array which is best, right? And best of x denotes the minimum length of a subarray having sum equals to x currently, right? So I know that I have scanned only the array from j1 plus 1 to n, right? So best of x denotes the minimum length of a subarray having sum is equals to x, but only after scanning elements from j1 plus 1 to n, right? Right now I am iterating on j1 in reverse order, so I have only iterated the array from j1 plus 1 to n. So this best of x is denoting the minimum length of a subarray having sum is equals to x, and this subarray is for sure in the half from in the half of the array from j1 plus 1 to n, right? So again I will write best of x in another manner which will make it more clearer. So best of x is the minimum length of a subarray in j1 plus 1 to n having sum is equals to x, right? And I know that this will be the case because I have only scanned the array from j1 plus 1 to n. So best of x denotes the minimum length of a subarray which has a sum is equals to x, and this subarray is completely in the half from j1 plus 1 to n, right? Okay, so yeah, so now when I iterate for I1, I have my I1 and j1 fixed, right? So I have I1 and j1 fixed. So let S1 be sum of I1 j1, and I can again find it using prefix sum in O of one time, right? So if I have a sum S1, I'll need to find another sum S2 which is in the second half from j1 plus 1 to n such that S1 plus S2 is equals to k, right? So basically I need S2 to be equals to k minus S1, and really what I want is my candidate answer is nothing but the length of the first subarray which is j1 minus I1 plus 1 plus length of the minimum size subarray which has sum equals to k minus S1, right? And this subarray is in j1 plus 1 to n, right? But if you look at it closely, you will realize that that is nothing but best of k minus S1, right? This and this are just the same thing for if you replace x with k minus S1, these two statements are totally similar. That is, best of k minus S1 is the minimum length of a subarray in j1 plus 1 to n having sum is equals to k minus S1, right? So my answer will be equals to minimum of answer and j1 minus I1 plus 1 plus best of k minus S1, right? And the only thing which needs to be taken care is to calculate this best array, right? This can't be done magically. But as it turns out, since we are allowed to have an O of n square time complexity, for a particular j, we can just keep updating this best array, right? And that can be done again in O of n time. And in totality, we'll have an outer loop and two inner loops which are not nested with each other. So our total time complexity will still remain O of n square. And this best array can again be updated very easily, and it will be more clear how to update it once I show you guys the code. So let's look at the code for now real quick. So this is the code for the third problem. the approach is the similar as to what I have discussed here. So first of all, we take the array as input and we construct the prefix sum array, right? And then we construct a best array, right? So I have initialized all the best values with infinity because right now we haven't even scanned the array at all. But best of 0 is 0 because obviously if we want a sum of 0, then we don't need to take any of the elements. Alright, so I initialize my answer with infinity and I start iterating my array from n to 0 in backwards order. So this I is the loop for j1, right? And uh, I will just assume that I have the best array updated for all the values from I plus 1 to n, and then I iterate for the first half for the beginning of my first subarray, and this is that loop. And again, what I'm doing is this temp is nothing but s1. This is the sum of my first subarray, and if I find out that this sum is less than or equals to k, then I can just do my answer as minimum of I minus j plus 1 plus best of k minus s1, and this s1 is nothing but temp. Now with that done, I have a task of updating the best array by taking into account the ith element, and that again can be done really easily. I can just iterate for all the values from I to n, and I know that all the subarrays which are starting from I plus 1 to n have already been taken care of. So the only arrays which need to be taken care of are the arrays which begin at I, right? So if an array is beginning at I, it can end at any point from I plus 1 to n. From I to n indeed. So I just iterate from I to n, and the sum will be j minus prefix sum of j minus prefix sum of I minus 1, and I only need to take care of the values which are less than equals to k. So I update the best of temp as the current best and the minimum of the current best and j minus I plus 1, right? And this way in O of n square I can solve the problem, right? And this is actually a well known technique called meet in the middle. And Ericto actually did a stream on this quite recently. So if you're interested in it, you can watch it. I'll probably provide the link to that in the description. Right, so this was the third problem, a really interesting problem. And yeah, so it had 3 subtasks, and solving all of them were really interesting rather than just barring the first subtask. The other 2 were really good. So yeah, all in all, a really interesting problem, right? Now with the first 3 problems done, I will be talking a little bit about the fourth problem, although I actually don't bother to solve very hard geometry problems. But the first subtask is somehow easy. It's just a simple construction which can be really understood very easily. So I'll just be talking about it for 2 minutes. It is not some very well made tutorial for this problem, but anyways, so basically what you have is you have been provided with the number n and a, and basically you need to find a polygon of n vertices which has an area of a by 2. Yeah, that is the only problem. And I'll be only talking about the first subtask, which is when n is up to 3 to n is from 3 to 5. That is, you're having either a triangle or a quadrilateral or a pentagon, right? So let's start talking about the construction. There is actually no intuition here. It's just hit and trial. And yeah, so let's talk about it. Problem D, first subtask. So the first case is when n is equals to 3, and this is really easy because also another constraint here is that all the points have to be integers. So all the points have to be integral here, and you need to output all the points of your polygon, right? So you need to find a triangle which has an area of 2a. I know that the area of any triangle is half into base into height. So if I just keep the base of my triangle as 2, then I can just form a triangle, right? But it's better to even keep your base as 1. You can do that as well. So just keep your base as 1, and you want this thing to be equals to a by 2, right? So really all you want is that your base into height is equals to a, and that is easy. So the construction here will be something like this. So this will be of size 1 and this will be of size A, and this is a right angle triangle, so automatically the area is going to be A by 2. And so the points can be like 0 0 1 0 and 0 comma A. So you can always output points like this: 0 0 1 0 and 0 comma A, right? And this is this case done when n is a triangle, and really there is not much intuition to talk about here. This is just hit and trial. So I'll just quickly tell how to do this for n is equals to 4 and 5. So now let's talk about the case when n is equals to 4. So also another thing to note here is that when n is equals to 3, all the values of A will give a valid answer, because I can have a triangle with area of half, and the minimum value of A is just starting from 1 if you look at the constraints. So the minimum area can be half, and I can actually successfully get a triangle of area half. So the answer will never be impossible when n is 3. Now let's talk about the case when n is equals to 4. So here one thing is that answer is impossible if A is less than 2, and that is because the minimum area of a square with all integer points is obviously going to be 1, right? Because the distance between 2 points having integer coordinates is greater than or equals to 1, and if the length and breadth of a quadrilateral are greater than or equals to 1, then its area is obviously greater than or equals to 1. So the area has to be A by 2, so A by 2 has to be greater than or equals to 1, so A has to be greater than or equals to 2. So the answer is impossible when A is less than 2, and when A is greater than or equals to 2, I can make a construction like this. So I know that an answer is possible for any type of triangle, right? So why not just make a 1 cross 1 square, and on top of it place a triangle, and once you are done with it, you just forget about this middle one. Oh damn. So basically what I'm doing is I'm forgetting about this middle line, and finally I'll be left with this figure, right? So this figure can be divided into a 1 cross 1 square, and the remainder is same as that this triangle, right? So below this triangle you just add a 1 cross 1 square and you forget about this middle line. I again drew that, yeah. So yeah, this will be my construction. So if you want me to mark the points, let's say this is 0 comma 0, then this is 1 comma 0, then this is 0 comma 1, and that makes this a 1 cross 1 square, and accordingly you want the total area to be equals to A by 2. So if you do the calculations, this point will probably come out to be 0 comma A minus 1, because if this point is 0 comma A minus 1, then the area of this rectangle would be A minus 1 by 2. The area of this rectangle would be A minus 2 by 2, and the area of this square is 1, so in total the area will become A by 2, right? So this is the construction for when n is equals to 4. Now let's talk about the case when n is equals to 5. So now this time we need a pentagon, and obviously a pentagon can always be divided into a quadrilateral plus a triangle, and the minimum area of a triangle is 1 by 2, and the minimum area of a square, as we talked about, is 1. So basically here the answer is impossible when A is less than 3, and that is because the minimum area as of a triangle is 1 by 2 and that of a square is 1. So the area is greater than or equals to 3 by 2, and the area is A by 2, so A by 2 should be greater than or equals to 3 by 2. That is why A has to be greater than or equals to 3. Right, with that done, let's just quickly talk about the construction. So it's somewhat similar. You just draw this figure which you drew for your square, and so for your quadrilateral you had something like this, right? So for your, while you were transitioning from a triangle to a quadrilateral, you drew something like this and you forgot about this middle line, right? So now again you drew the previous figure and then you forget about this straight line here and you make a triangle like this, right? So now you have forgotten about this middle line, right? And the points are going to be 0 comma 0, again 1 comma 0, and this point is going to be 2 comma 2 every time. So if this point is 2 comma 2, then the area of this triangle comes out to be 1, and similarly the area of this square comes out to be 1. No, I'm sorry, the area of this triangle comes out to be half, right? The area of this triangle is half and the area of this square is 1, and the area of this rest of the region I need to make something, and if I choose this point as 0 comma a minus 3, then this will all add up, right? Because my area will become what? So if I look at the above square, then the area will be half into a minus 4 plus the area of the square is 1, and this area of this triangle here is half, right? So essentially this area will come out to be a by 2 if I'm not wrong. Yeah, this area is coming out to be a by 2, and yeah, that pretty much does the job, right? So this is how you can actually solve this problem. It's just some easy constructions, and yeah, so with that I guess the solutions to all the problems that I wanted to talk about are done, and so I hope you guys got to learn something today as well, and I'll see you guys in the next video. Thank you for watching till the end. Bye bye.